All right, welcome to day 2 of distance learning. I hope you guys are doing your best to make the most of these circumstances and learn as much as possible in a new environment. I'm proud of you guys for the effort you guys are putting in. I'm excited that I'm learning new things about some distance learning, and I hope you are too. Today we're going to continue our look at logarithmic functions. Yesterday we introduced you to the definition of a logarithm, which I'm going to refer to many times today. Today we're going to look at graphing logarithms and solving some logarithmic equations. So, the objective that we can graph logarithmic functions. Before we actually begin graphing, I need to give you a little background reminder, some prior knowledge from last year, but worth reminding you. Some logarithms are used so much that we have abbreviations for them. Okay? One of those is the natural logarithm. Now, a natural logarithm is a logarithm whose base is e. Remember, we referred to e as the natural base. This is an irrational number. It occurs in many, many applications. Over here, you see that I've got the definition of logarithm that I showed you a moment ago, rewritten where the base is e. So this was our definition, where I had an arbitrary base a. Now it's rewritten with a base e. If you see the ln notation, we don't actually read that as ln, we read that as the natural logarithm. So y is equal to the natural logarithm of x if and only if x equals e to the y power. Okay? The other notation you'll see frequently is what we call the common logarithm. Right? The common logarithm is a logarithm whose base is 10. When you have a common logarithm, the shortcut mathematicians use is they don't show the base. So anytime you are working with a logarithm and you see the log, but you don't see the subscript for the base, you can assume that the base is 10. There are buttons on your calculator for both natural logarithm and common logarithm. And for most of you, those are the only logarithm buttons that are on your calculator, base e and base 10. Okay. With that out of the way, we're ready to start graphing logarithmic functions. And our ability to graph logarithmic functions is based on our knowledge that logarithmic functions are the inverse of exponential functions. And since exponential functions are one-to-one, we know that their inverse will also be a function. To start that exploration, I'm going to have you look at these two graphs here. Okay? These are both graphs of exponential functions. The one on the left is y equals a to the x power, where the base a is between 0 and 1. So that's a positive base, but less than 1. We've talked about how that gives us an exponential decay, and the function is decreasing. The other graph over here on the right is also y equals a to the x, but this is for bases where the a value is greater than 1. We talked about how this will be an increasing function, and this gives us our example of exponential growth. For both of my two graphs right now, the table I have in the middle represents 5 points on each curve. You can see my x's, I've chosen -2, -1, 0, 1, and 2, and then I've substituted those x's into my y equals a to the x power to get 1 over a squared, 1 over a, 1, a, and a squared. If you need a quick reminder about the graphs of exponential functions, look at your notes from our previous section on exponential functions. You can also look at page 283 and 285 in our Sullivan and Sullivan Pre-Calculus book. Those pages have yellow boxes that detail all sorts of things about these functions. The fact that the domain of each is all real numbers. The range is the open interval from 0 to infinity. They have horizontal asymptotes at y equals 0. They have y-intercepts at 0, 1. They don't have x-intercepts. They're both smooth and continuous. They're both one-to-one functions that pass the horizontal line test. All kinds of things that we review on page 283 and 285. Okay? But now our purpose is we want to graph the inverse of these functions. So remember, to graph the inverse of a function, for each ordered pair on the function, I need to interchange the x and y coordinate. So if the exponential function y equals a to the x power contains the point -2, 1 over a squared, when I switch that and I interchange the x and y, I'm going to get the ordered pair where the x coordinate, let me write this, is 1 over a squared, and the y coordinate is -2. Okay? In the instance where 1 over a squared is using an a that is very close to 0, between 0 and 1, then 1 over a squared is actually going to be a very large number. So I'm going to get a very large number there as I graph that. Okay? As I continue down my chart, 1 over a, comma, -1, 1 comma 0, a comma 1, oh sorry, f, g, h, I, and j at a squared, comma 2. So now I can graph all of these points on my graph, and I'm going to begin to see the shape of the inverse function. Okay? So let's start off with the one on the left where we're using a between 0 and 1. Okay? We'll start with our ordered pair 1 over a squared, comma, -2. That's going to be a very large number down in here. I may even kind of leave it off my graph and come back to it. Maybe it's better if I start here at a squared, comma 2. All right. A comma 1, one comma 0, 1 over a, comma, -1, and we talked about that 1 over a squared, comma, -2, maybe more out there. Okay, and that's my graph of y equals a logarithm base a of x. If I look at those two graphs are going to have symmetry across the line y equals x. Very similar situation over here where a is greater than 1. This may make a little more intuitive sense. Oh, I'm sorry, I didn't label my points. All right, this was F, G, H, I, J. Okay, so when I graph over here, when I graph the ordered pair 1 over a squared, comma, -2, now this makes a little more intuitive sense for you. Okay, 1 over a, comma, -1, maybe even more in there, 1 comma 0, a comma 1, and a squared, comma 2, we get that curve for y equals log base a of x. Again, our two graphs have symmetry across the line y equals x. One is a reflection of the other. In both of my original graphs, I had a horizontal asymptote at y equals 0. Since I'm using an inverse function now, I'm going to get a vertical asymptote at x equals 0. And we can see that in both our graphs. I also see that you couldn't quite see the bottom of my table there. I apologize for that. This might be a good time for you to pause the video, take some time to look at page 283 and 285 for characteristics of exponential functions. Then look at the bottom of page 298 for properties of the logarithmic graphs that we just drew. And make sure you have both of these pictures in your notes as well. These two pictures are figure 36A and 36B on page 298. You're going to be paused for quite a while, and we'll see you in a minute to do an example of graphing. All right, we're back with the first of two relatively lengthy examples on graphing logarithmic functions. So this is example 6. We're going to graph the function the negative natural log of the quantity x minus 2. All right, the negative natural log of the quantity x minus 2. Okay. In this example, the book asks us parts A, B, C, D, E, and F. There's a lot of work to do. The first of those, part A, is to find the domain of the function. So yesterday we said that the argument of a logarithmic function must be greater than 0. In this problem, the argument is the quantity x minus 2. So if x minus 2 is greater than 0, then adding 2 to both sides tells us that x must be greater than 2. And the domain of this logarithmic function is the open interval from 2 to infinity. All right, there's our domain. In part B, we are asked to graph function f. Now this is going to be a relatively lengthy process. I kind of warned you about that at the beginning of the example. So to graph this function, the first thing I need to do is consider the parent. All right? Remember, the parent is the simplest function in a family with all the characteristics of the family. So the function I'm given, f of x, is a more complicated natural logarithmic function. The parent function is just y equals natural log of x. In order to graph this parent function, I need a table of values, and I'm just going to present that to you as a whole. There's our table of values. Okay? And you'll say, well, where did he get that so quickly? Remember that previously we have graphed the function y equals e to the x power, the exponential function with the natural base. Because the logarithmic function is the inverse, all I did is interchange the x and y columns from that table to get this table. All right? I would remind you that this has to have a vertical asymptote at the line x equals 0. That should make sense when you think about the domain of the parent. Okay? So now our job is to take this parent function and transform it to get function f of x. So looking at function f of x here, I can see that there are two transformations happening. According to the order of operations, the first transformation is inside the argument. X subtract 2 tells me that I'm going to translate my parent function right 2 units. After that, the parent function, which was the natural log, will occur, meaning that every other transformation is going to affect the y coordinates. Our last transformation is that coefficient -1, which reflects us over the x-axis. Okay? In order to get those transformations into my table of values, anything before the parent affects x coordinates. So in my table of values from the parent function, I'm going to need to slide that up a little bit. Sorry about that. For my x coordinates, I'm going to translate all 5 points from the parent function's x coordinates right 2 units. Obviously, 4 of these 5 are irrational numbers. If you want to see approximate values, you can use your calculator to do so. For the y values, I know that I need to reflect over the x-axis. That requires me to multiply by -1. So here are the y values from my parent function multiplied by -1. Okay. Why don't you pause the video here for a minute and make sure that you understand both of these tables and the transformations. After you unpause, we'll look at the graph. All right, we're back and we're ready to look at the graph of our function. So I'm going to try and keep my table on the screen. But we can see how this table leads us to this graph. All right? When we had stated that the parent function had a vertical asymptote at x equals 0, obviously translating that to the right 2 units gives us a vertical asymptote at x equals 2. And then I have just graphed these 5 points, labeling them with the values from my table. Pause the video if you need time to write down that graph, and then we'll talk about some characteristics of the graph. Okay. So after graphing the function, the next thing we are asked in part C is to determine the range of the function and the vertical asymptote of the function by using the graph. Well, we can see that the range of that function is all real numbers, because as we draw that function, we can substitute in x's to give us y values as little or as great as we desire. The vertical asymptote is x equals 2. Again, we talked about the transformation from the parent function that causes that to happen. In part D, we are asked to find the inverse of the given function f of x. What I have done is I have already shown the interchanging of the independent and dependent variable. So this is the interchanging of x and y that leads me to the inverse of the given function from the example. Obviously now we've got to perform some algebra to solve for y. So what I'm going to do, I'm going to multiply both sides by -1. That gives me negative x equals the natural log of the quantity y minus 2. And then it's time to go back to our definition of logarithm, which keeps popping up over and over and over and over, and rewrite this in the equivalent format. I know that the negative x equal to the logarithm means that negative x is the exponent that goes on the natural base to produce y subtract 2. Adding 2 to both sides of the equal sign, now I have y isolated. Y is equal to e to the negative x power plus 2. Because the original logarithmic function is 1-to-1, that guarantees that the inverse is also a function, so I can use my notation. The inverse of function f is e to the negative x plus 2. Go ahead and pause the video if you need time to write down the work for the inverse of the original function. All right, next order of business, we are asked to find the domain and range of the inverse function. If we think back to our study of composition of functions and inverse functions, we know that the domain of a function is the range of its inverse. And so we were told, actually we did the work at the beginning, to find that the domain of our logarithmic function was 2 to infinity, therefore that is the range of the inverse. We also worked at the beginning of part C to find that the range of the logarithmic function was all real numbers, therefore it is the domain of the inverse. And finally, we had stated that the logarithmic function had a vertical asymptote at x equals 2, then it makes sense that the inverse has to have a horizontal asymptote at y equals 2. With all that knowledge, the last thing that we're going to do is we're going to graph the inverse function, all right, the exponential function. And when we graph that, we can use a table of values. This table of values was created by simply copying the table of values from part B and interchanging the x and y coordinates. Again, the exponential function is the inverse of a logarithmic function, so by interchanging the x and y coordinates, we create the table of values here. I have graphed those, and you can see how the listed domain, range, and horizontal asymptote correspond to this graph here. Go ahead and pause the video and make sure you are comfortable with this graph of the exponential function. All right. Last thing I'm going to say about this example before we move on. Remember that all exponential functions have a domain of all real numbers. Therefore, they do not have any vertical asymptotes. They have only horizontal asymptotes. That means the inverse, the logarithmic function, which we worked with first, will always have a vertical asymptote and no horizontal asymptotes. You can use the presence of an asymptote to help you quickly decide whether a graph represents an exponential or a logarithmic function by looking for a horizontal or a vertical asymptote, respectively. If you are working along in Sullivan and Sullivan's pre-calculus book, I would like you to pause the video and attempt all of example 7 on your own. Example 7 is very similar to example 6. We are going to do all of the same parts with a different logarithmic function. We are going to do parts A through F with 3 times the common logarithm of the quantity x minus 1. Remember that common logarithms have a base of 10 that doesn't need to be shown, it's implied. So pause the video and try all 6 parts of example 7. Okay, I hope that you gave that your best effort. Let's take a moment and check. Part A is to find the domain of this logarithmic function. The argument must be greater than 0. Therefore, x minus 1 is greater than 0, and we solve to find that x must be greater than 1. Our domain is the open interval 1 to infinity. The next step is relatively lengthy. It's our work finding tables of values for the parent common logarithmic function and the transformed function from example 7. I got my values for the parent function by switching the x and y coordinates of the function y equals 10 to the x power. When I transformed it, I moved all of those x coordinates right 1 unit, and I vertically stretched all of the y coordinates by a factor of 3, so I multiplied each of these y coordinates by 3. Once I have those, then I'm able to graph this logarithmic function. In part C, we are asked to find the range and the vertical asymptote of the logarithmic function. The range of that graph is negative infinity to positive infinity, all real numbers. And we had a vertical asymptote at x equals 1 due to the translation 1 unit right of the parent common logarithmic function. In part D, we are asked to find the inverse, so I've labeled my work for the inverse, and I've interchanged my x and y variable, my independent and dependent variable. Solving for y is very similar to the process we did in the previous example. Pause the video for a moment if you need, and check the work for the inverse function. Next, we were asked to find the domain and range of the inverse function. Remember that the domain of the inverse is the range of the original function, and the range of the inverse is the domain of the original function. We found both of those earlier. We also know that if the original logarithmic function has a vertical asymptote at x equals 1, then our inverse must have a horizontal asymptote at y equals 1. With all that information in hand, we can create our table and graph for the inverse function. The table that you see here is the table from the part B, where we graphed the logarithmic function with all the x and y coordinates interchanged. Again, you can see the domain, range, and horizontal asymptote that we mentioned a moment ago. I'll give you an opportunity to pause the video here and make sure you're comfortable with this graph. Okay, our last objective as we study logarithmic functions today is that we can solve logarithmic equations, right? Remember that a logarithmic equation is an equation that contains a logarithm, and solving means to find the value of the variable that makes that equation true. So we're going to look through multiple examples of solving logarithmic equations. The first example, this is 8a from our Sullivan and Sullivan textbook, tells us log base 3 of the quantity 4x minus 7 is equal to 2. Our unknown value, our variable, is in the argument. When the unknown is in the argument, you're frequently going to benefit by using the definition of logarithms to rewrite this equation. So if I use my definition of logarithms to rewrite this equation, instead of writing it as a logarithm, I can write it as a base with an exponent. The base is 3, and the logarithm is always equal to a specific exponent. So now I have 3 to the second power equals 4x minus 7, and that's an algebra 1 problem we can solve very quickly. Squaring 3 gives us 9. Adding 7 to both sides of the equation gives us 16 equals 4x, and dividing both sides of the equation by 4 gives us x equals 4. Now, before I highlight that answer, the other thing we need to talk about with logarithmic equations is that logarithmic equations can have extraneous solutions. Therefore, it's not optional that we check our answers to all logarithmic equations. This is not me being picky. We need to make sure that we have not found an extraneous solution. If I substitute my value 4 in place of x and begin to simplify this, 4 times 4 subtract 7 gives me an argument of 9. So I'm asking, is log base 3 of 9 equal to 2? Using my definition, yet again, to rewrite this, asks if 3 squared is equal to 9. And of course we know that yes, 9 is equal to 9, and this checks out. So I can highlight my solution, but only after checking. Okay. Example 8b gives us another equation involving a logarithm. The difference between 8a and 8b is that in 8b, the unknown is in the base of the logarithm instead of the argument. With the unknown in the base, I'm going to refer to my definition again, and I'm going to rewrite my logarithmic equation using an exponent. X squared equals 64. Again, now an easy algebra 1 equation. Square root both sides of my equation tells me that the square root of x squared is equal to plus or minus the square root of 64, and thus x is equal to positive or negative 8. As I think about this problem, though, I'm reminded that we have stated earlier that the base of a logarithmic function must be positive. Remember, we learned about logarithms as the inverse of an exponential function, and in order for an exponential function to have a domain of all real numbers, the base must be positive. Therefore, I can conclude that the base of a logarithm must be positive, and that x cannot equal negative 8. Because the base of my logarithm cannot be negative 8. Therefore, the only solution that I'm going to check is x equals positive 8. When I check that, I substitute positive 8 into my logarithm. I use my definition to rewrite, and 8 squared does equal 64, and we check this answer. Example 8c is different from the other two, in that now the equation is e to the 2x equals 5, and there is no logarithm present. This is an exponential equation, not a logarithmic equation. We've stated that finding the value of an unknown exponent is a challenge for us until we understand logarithms fully. So for the third problem in a row, I'm going to rely on my definition, only this time I'm going to begin with an equation in this form, and I'm going to change to an equation in logarithmic form, saying that the natural logarithm of 5 is equal to 2x. Remember, a natural logarithm is a logarithm whose base is the natural base, e. In order to isolate x, all I need to do now is multiply both sides by 1/2. And I have 1/2 times the natural logarithm of 5 is equal to x. I've made a note that this is the exact solution to the equation. This is an irrational number. Many of you may not be certain exactly where that falls on our real number line. If you wish to approximate it, your graphing calculator has a natural logarithm button, and we can see that this is approximately equal to 805 thousandths. You'll notice that I've already highlighted these answers without checking them. Remember that the domain of an exponential function is all real numbers. There is no reason for me to check these answers. If you need to pause the video at any point through these last 3 examples to make sure you have time to write them down, please do so. We have one real-life application left, and we'll be done with this lesson. All right, last application is an application about the relative probability of getting into an auto accident based on one's blood alcohol content expressed as a percentage. And this is example problem number 10 in Sullivan and Sullivan's pre-calculus textbook. It's on page 303. If you're following along in your textbook, this would be a good time to pause the video and read the entire original problem. After reading this scenario, we should be able to define our independent and dependent variables. The independent variable x is the percent of concentration of alcohol in the bloodstream, commonly referred to as BAC. The dependent variable r is the relative risk of an accident. With this problem, the first thing that we're going to need to find is we're going to need to find the value of the constant k in our exponent. It is given to us that research indicates that the relative risk of a person having an accident with a BAC of 2/hundredths of 1% is 1.4. By substituting those values into our given equation, we can solve for the value of the constant k. In order to do that, I'm going to use my definition. Boy, how many times has that popped up today? To rewrite this as a logarithm whose base is e. Remember, that's a natural logarithm. So my exponent is equal to my logarithm. Then, in order to isolate k, I can divide both sides of the equation by 2/100ths. Dividing by 2/100ths is the same as multiplying by 100 over 2, which is just multiplying by 50. So the constant here in the exponent is 50 times the natural logarithm of 1.4. Now, if you're following along with the textbook, Sullivan and Sullivan approximate this constant at this point. I'm disappointed with this decision. There's no reason for us to approximate this constant before going on to use it. Our work will be more accurate if we leave the irrational number in its exact form. So I will use the constant 50 times the natural log of 1.4 for all calculations moving forward. In part B, we are asked to find the relative risk if the BAC of the driver is 17/100ths of 1%. Here's my independent variable, 17/100ths. Here's my constant found from above, and I see that my right-hand side is now a constant. There is no variable on the right-hand side. So approximating this gets me a relative risk of 17.462. Based on my definitions of the variables above, what that tells me, I'm going to slide up slightly, is that for a BAC of 0.17%, a driver is about 17.462 times as likely to have an accident as someone who has a BAC of 0. That's what we mean by relative probability. Pause the video now and make sure you're comfortable with parts A and B. In part C, we are asked for the BAC of a person who has a relative risk of getting in an accident 100 times greater than a person who has not been drinking. Obviously an incredible risky person. In order to solve this equation, I need to isolate my exponent, and so I'm going to use my definition of logarithms again to rewrite this as a natural logarithm. Here's my exponent, my constant, 50 times the natural log of 1.4, multiplied by the unknown concentration x, equals a logarithm whose base is e of the argument 100. To isolate x, I'll divide both sides by my constant, 50 times the natural log of 1.4, and now I have isolated x. I can use my calculator to approximate this quotient of two natural logarithms, ending up with an approximate solution of 274 thousandths. Based on my definition of my variables from earlier, that means that a person is 100 times as likely to have an accident if their BAC is approximately 274 thousandths of 1%. This is over triple the legal limit for DUI in the state of Colorado. Speaking of DUI, the last of the examples, example D, tells us that the law determines that a person who is 4 times as likely to have an accident should be considered driving under the influence. They ask us to use a relative probability of 4 to calculate the BAC of a person who should be charged with DUI. This problem is very similar to the previous portion, part C, where I had a 100 here. The only difference is that now I'm using a 4, but my process for solving remains the same. I use the definition of logarithms to rewrite my equation as a natural logarithm. I divide both sides of the equation by my constant, and I approximate on my calculator. Based on my variable definitions above, this tells us that a driver with a BAC of approximately 82 thousandths of 1% or greater should be charged with DUI. This is the legal limit for DUI in the state of Colorado. Our application here is valid in the real world. I know that this was a long video, almost 40 minutes long. Thank you guys so much for listening to me talk about graphing logarithmic functions and solving logarithmic equations. I hope that you continue to do your best to learn material while you're out of school. I hope that you continue to stay healthy. You all are very important to me. I'm thinking about you every day. I hope to see you all soon. Have a good day.